We talked last time about, we ended up with a situation where we had a steady state circuit, and we were talking about the electric field in the steady state circuit. But we said there was an issue with the electric field being created solely by the battery. And so we're going to look at that in a little bit more detail. And there's this worksheet that we just handed out. If you haven't picked one up, they're at the front here, where it shows an example of a circuit with a battery. And again, we're using this kind of crude model of a battery. We're just thinking of it as two plates of a capacitor, one positively charged, one negatively charged. And then some way of maintaining that charge separation, so there's a conveyor belt driving charge from one end to the other. And then the circuit is just a single wire, but it has a bend in it. Let's see if I can kind of draw it. And something like that. Okay. All right. I didn't draw it too well, but it's meant to have the same thickness of wire for the entire circuit. Okay, so it's just a single wire, single thickness, single value of electron density and electron mobility. So here's what I want you to do. On the top part of the diagram, and in fact there may be even a question here, we can talk about this. On the top part of the diagram, just take a minute or two and draw the drift velocity of electrons in the steady state. Okay, so if we're thinking about the circuit's hooked up, it's been running for a while, we're in a steady state. Remember, a steady state means that it's not changing anymore, right? The electron velocity, or the drift velocity, is not equal to 0, so there's going to be some moving electrons. And we also know the current node rule, which says that the current in is equal to the current out, right? Current conservation, or charge conservation plus the steady state, says that current is equal to current out. And then we also know I is equal to N, A, V, and V is equal to U, E. So just reminders there. So just take a minute, draw the arrows, draw the the velocity vectors that represent the electron drift velocity at each little x on the top part of the diagram. Okay, so we've basically got this. So you should have something. Well, first of all, what's it look like? The electron. So it's location 2. Which directions are the electrons moving? They're moving toward the battery or away? They're moving away from the battery. Remember, you can think of the negative terminal of the battery as the electrons are coming from the negative terminal and moving that way, away from the negative terminal throughout the circuit. And then it kind of twists around here. And how should these arrows, what should be the relative lengths of these arrows be? They should be the same, right? Because if we're in a steady state, we have the same current everywhere, which means given the same thickness in N, we should have the same drift speed everywhere. So you should get something that looks like that, right? So I saw most of that. A couple people had the directions reversed, but we all basically had the same diagram. So on the same picture, given that in the steady state the velocity has to be this, what should the electric field be at each of those locations? So draw the electric field vectors at each little x. What do we think? The electric field should point in what direction compared to the electron drift velocity? Opposite direction, right? Because these are electrons. The force is going to be in the opposite direction of the electric field. So E be pointing that way. And what about the relative magnitudes of the electric field vectors? Should be the same everywhere, right? Because if we have the same drift speed from V equals UE, we should have the same electric field. So we have E pointing that way, and then that way here, and then that way here, and so on. Okay? So you end up with something that looks like that, right? You should have something like that on your diagram. Okay, so now here's the question. We know what it looks like in the steady state. But let's think about sort of the first instant after you connect the circuit together. So we're really going to be talking about what we called last time a transient situation, where we're going from equilibrium, where there's no current flowing, and eventually reaching a steady state. And that it happens almost instantaneously, but there is a small amount of time where things are changing. And so initially we have the charge on this battery, like two plates of a capacitor. It looks kind of like a dipole. We talked about that last time. So think about if we assume that initially the only charges are on the battery, they're the only ones here, what would the electric field look like at each of those locations? So on the bottom diagram, the second picture on the bottom, draw an arrow representing the electric field due only to the charges on the battery at each of those x's. Think about what the field due to that charge distribution would look like at each of those locations. It's okay to be wrong here. Let me emphasize this. It's actually useful to go through and expend the mental energy to try this out. Okay, again, just think of it as a dipole. Okay, you have a positive charge on one end, right? Negative on the other. How do we calculate the electric field, or at least just work out the directions of the electric field of a dipole on the axis and then on that perpendicular axis? In some way, we're sort of just ignoring the presence of the wire for just a second and just looking at those particular observation locations. So try it out. Okay, I think we're getting the basic idea. So let's talk about this. Let me just erase my other vectors because I don't want to draw the whole thing again. So it's a dipole, right? And on the axis of the dipole, so this location and this location, if we're on the positive side, the electric field should be pointing in what direction? Everybody, that way. All right. And on the negative end, it should be pointing same direction, right? And again, you can work that out, but add up the field due to the positive and due to the negative, and then on this side, the field due to the positive is larger, that points away, and the field due to the negative is larger here, that points toward. If you're on the perpendicular axis here, at this location, this location, this location, the field here should be pointing that way, yeah. And the field here should be pointing same direction. How's the magnitude compare? Should be smaller, right? And then the field here should be same direction but smaller. Okay. So let's look at what we have now. And we got something like this, right? Well, let's take these electric fields seriously and think about what would happen to the mobile electron C. Specifically, you've got fields here pointing in these directions. Draw the drift velocities. What would the drift velocities look like at those particular locations? You can do it on the same diagram. Okay, what do we got? What do we got? The electric field is exerting a force on these negative charges. So at this location, the velocity is what direction? Opposite, okay. And at this location, the direction is opposite. And at this location, the direction is opposite. And as a couple of you mentioned, the velocity and the electric field are proportional to each other. So if I have a bigger E, I should have a bigger V, and a smaller E, I should have a smaller V. Okay? And then here I have a velocity that points in the opposite direction. And here I have a velocity that points in the opposite direction of E. Okay? That's what the electric field is telling us. It's giving us how it's going to be moving the electrons through the wire. But we've got a problem, right? Because this certainly isn't what we have in the steady state. And specifically, we've got electrons moving in opposite directions in different parts of the circuit. Well, again, let's sort of follow our noses. Okay, here's the pattern we should get. What's going to happen if you actually? So here is we're marking this the left bend. Okay, so this little curve here is the left bend of the circuit. We'll call this the right bend of the circuit. Think about the direction of those electron velocities. In the next tiny fraction of a second, what will happen at the left bend of the wire? Is nothing going to change, or is there going to be a change in the charge? Will it become more negative, or will it become more positive? Okay, if electrons are moving from point 5, they're moving toward the left bend, and from point 4, they're moving toward the left bend. So that means we must have a buildup of negative charge. Okay, where is that charge going to end up? Is it going to live inside here? On a conductor, where can the excess charge be? Only on the surface, right? So we're going to end up with some surface charge. We're going to end up with this left end of the circuit having some excess electrons on that end. Okay? That's the only possibility. And if that's the case, well, we just answered this. Okay? The electrons have to be on the surface of the wire, not inside. Okay? If they were inside, they would just be repelled by each other until they reach the outer surface anyway. Well, okay, what do you think is going to happen at the right bend? Just call it out. It's got to get more positive, right? Because electrons are leaving this end and electrons are leaving this end. So we're going to have a deficiency of electrons over here. So we end up with an excess amount of positive charge. Okay? Well, and we talked about that. Okay, it's got to be on the surface. Well, if we have excess charge on the surfaces of the wire, those excess charges create an electric field inside the wire, right? So if we're thinking about let's look at location 4, okay, so just directly in between the right bend and the left bend. What's going to be the direction of the electric field due only to those charges we now have on the surfaces of the wire? Okay, well, not quite as much agreement as we had last time. Most of us are saying that the electric field due to those surface charges is going to point to the left. Well, you've got a positive charge over here. Fields due to positive charges point away from positive charges, right? Fields due to negative charges point toward negative charges. So it looks like if I'm looking at the field due just to those surface charges, that's going to point to the left. Okay. So we have the original field of the battery. We now have an electric field due to the surface charges. And, well, depending on how long we wait and how much charge builds up here, we can get a situation where we end up with the sum of these two electric fields being E net pointing in the direction we need it to point in the steady state, right? So what's happening is the field just due to the battery causes charges to move. Those charges move, and they may move in funny ways until surface charge builds up on the surface of the wire. Okay? Those surface charges themselves create their own electric fields, and this keeps happening until finally stops when we reach what? The steady state. It finally stops when we reach the steady state. And that steady state has got to be a situation where we have the net electric field pointing in the correct direction to drive the current in the correct direction. And eventually we reach a point where all those electric fields are, in fact, in this particular situation, equal to each other, and the velocities are equal to each other. Okay? But the point is, and the whole idea behind this little exercise is that it's not the battery alone that's creating the net electric field inside the wire that's driving the charges. There's also surface charge on the wires themselves, and it's a feedback mechanism. Okay, the electric field causes the surface charge to build up, which changes the electric field, which changes the distribution of the surface charges, and it keeps happening over and over until you reach the steady state situation. And it could happen, again, almost instantaneously, but it's there, and it's present, and it's the only way to make, to get the electric fields to point in the correct direction in the steady state. Okay? Let's see. So we end up, okay, so we just drew that. That's the situation we ended up with. And this apparently is, in this picture, it's not enough to change the direction of the net electric field, but after a while, once more charge builds up, you end up with a larger electric field and a net electric field pointing in the correct direction. Okay? That's ultimately what we have to end up with, and this picture is just showing a possible, representation or just a schematic representation of what the surface charge on the wire might have to look like. Okay, and so we end up with a lot of positive charge near the positive end, and that positive charge diminishes a little bit, and then we draw a few less positives here to show that that positive charge is going down. A few less positives here to show that it's even less. And then at some point, the charge distribution goes from positive to negative, and the amount of negative charge goes up until we reach the other end. And this is called a gradient, namely a surface charge gradient. Meaning that, gradient meaning a change, right? A continuous change over distance. And so the density of the charge is on the wires is, to a first approximation, it can be a little more complicated than what we're letting on here, but overall the density of the charge on the wires has to change as you move around in order to get the electric field to point in the correct direction. How does that work? Well, let's look at a wire just for a second. Let me just look at sort of two strips of the wire. We'll look at a little strip here, kind of a ring, and another strip here, another ring. And let's say the surface charge is changing. So we have a lot of positive charge on this ring. Okay. And let's say a little bit of positive charge on this ring. Well, if I were looking at a point halfway in between both of them, and I wanted to draw the electric field due to the ring on the left side, that electric field would be pointing in what direction? Pointing that way, right? Pointing away from that positive charge. Let's say E due to the left. The field due to the the electric field due to the charged ring on this side would be pointing in what direction? Opposite, right? But how would its magnitude compare? Be smaller, right? So we end up with electric field due to the right end pointing that way. But overall, because of the difference in charge, because the charges are not equal, and so the fields don't cancel out, you end up with a net electric field pointing in this direction. Okay, so we're just looking here at the surface charge gradient, not at the battery, but we can make a sort of a plausibility argument of how this change in the surface charge spread out over the wire can lead to a net electric field. And just to show that in more detail, we have a program here which is just going to go through and do the brute force calculations using the superposition principle of electric fields at various locations, modeling a wire as just a series of rings of charge. Okay, so on this end where it's more red, the reddish color indicates positive charge, the bluish color indicates a negative charge. And so we're going from lots of positive, and then where it's neutral color, it's kind of zero charge, and then it goes more blue, and that's negative charge. Okay, So these are just modeling as a series of point charges. I'm going to remove the point charges just to make it easier to see. And then we do the calculations. The computer is just doing the superposition principle for each of those locations inside. And so outside we get some net electric field pointing away from the surface charge, but inside you see that the electric field points along the direction of the wire, and it's uniform. For a uniform thickness and a uniform material, the electric field is a constant. It doesn't matter whether we're in the interior or near the edge. The field is mostly uniform, essentially uniform, inside the wire. Okay? And so this is just showing how we have a surface charge gradient leading to a net electric field inside the wire which can drive the current. Okay? And the bigger the gradient, generally speaking, the bigger the electric field. Okay? Let's, for example, take a look at a situation. Okay, so we basically just talked about this, but if you had a uniform charge, if all the rings were uniformly charged, the net electric field would be 0. But if you have this gradient of charge where it's more positive on one end, more negative on the other, you're going to get a net electric field pointing in what direction? 7, right? It's going to be pointing in direction 7. Okay. Similar sort of situation here. I want to look at a specific circuit. Let's just do a quick review of what we did last time. Here's a circuit where we have a thick wire and another thick wire connected to each other by a thin wire, and it's all the same material. And just review of what we talked about last time. What do we know about the current in the thick wire versus the current in the thin wire, the electron current? All right, well, maybe some of us need a little bit of review on this, but the current, if we're in the steady state, what do we know about the current in and the current out of a node? They've got to be equal. They've got to be equal, okay? So you have the same number of electrons flowing into the thin wire, I guess going this way, into the thin wire per second as you have them flowing out of the thick wire per second. The currents have to be equal. But what's different? What would have to be different if the two currents are equal but the thicknesses are different? What's different? Drift speed will be different, yes, because I1 is equal to I2. So NA1 V1 is equal to NA2 V2. Drift speeds would be different. And also, therefore, okay, cross-sectional areas are different. One more thing, V equals UE. If the drift speeds are different, then electric fields are different. Okay, you're going to have a bigger drift speed in the thinner wire, right, than you have in the thicker wire. Bigger electric field. So what's that tell you about the surface charge gradient? Where is there a bigger change in surface charge per unit length? We're on the thick wire. The thick wire has a smaller field, right? So you should have it on the thin wire, right? And so I would draw something like this. I'd have a big change in the surface charge density across the thin wire, and then across the thick wire, maybe not so much, okay? So, again, drawing these schematic diagrams just to show a general sense of how much charge you have at each point. You want to show that there's a bigger charge change across places where you have a larger electric field. That's the key idea, okay? All right, next time we will do some more complex applications of circuits.